Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our questions for today's session. Okay, so question 1 asks to predict the ideal bond angle or angles around each central atom in this molecule. Okay, so let's draw out the molecule and find out which parts are the central atoms. So we have a carbon that has a triple bond to a nitrogen. It's kind of has like a cyanide functionality. And then we have this amine at the end. And our two main central atoms would be the nitrogen, how it's bonded to two hydrogens and a carbon. And then our second central atom would be the carbon in between the two nitrogen. Okay, so first let's look at the amine. And I'll just redraw this. So if we look at the structure of this compound, we're mainly interested in how many bonding pairs it has and how many lone pairs it has. So by bonding pairs, it means like a bonding group. So in the case of this nitrogen, it has 3 bonding pairs, the carbon and the 2 hydrogens. So I'm just going to write 3 bonding pairs. And you'll notice it also has 1 lone pair. Okay, so the question asks to predict the ideal bond angle. And to do that, I'm going to look up something called the Vesper model, or like this chart, that predicts the type of shape, molecular shape, that this central atom might have. Just trying to find one that has like a good, I'll just search chart. That might be too small to read. Okay, so here is an example of what a Vesper chart might look like. I'm going to find one that has more options though. But typically these charts might be given to you in a question, or they would tell you to refer to it in a table. But basically they all kind of say the same thing. Let's try this one even though It's like small. Okay, so basically you'll see that the chart kind of looks like this. They have the total domains, the generic formula, and kind of like a diagram of what it might look like. There's a column that says how many bonded atoms it might have, how many lone pairs it might have, and then it gives the molecular shape, electron geometry, and example. But this one still doesn't have the bond angle. Let me just search bond angle. This one might help. Okay, so this is pretty helpful. So three bond pairs and one lone pair gives us this like bent shape. Yeah, so this one's a nice and detailed one. So here big one. Okay, so three bonded atoms and one lone pair gives us this trigonal pyramid molecular shape. I'm just going to write that down. The electron geometry is a tetrahedral. Its hybridization would be sp3. And for bond angles, it is around 109.5 degrees. Okay, so now let's look at the second central atom, which is the carbon, as the triple bonded nitrogen and then a single bonded nitrogen. Okay, so again, let's count how many bonding pairs it has, or bonded atoms it has. And if we count, we see it only has 2 bonding pairs. And it also has 0 lone pairs. So if we go back to our Vesper theory chart, you see here, when the central atom looks like this, it's almost like it's linear. So its molecular shape is linear. And we can also predict that because the carbon has a triple bond, so it prevents a lot of the different angles you might have. So typically, it's quite common to see that a triple bonded atom might give a bond angle of around 180 degrees. And we can also just see that in the picture as well. So if we look at this bond angle, it's 180 degrees. Okay, so let's see what the junior tutor said. For the prediction of the ideal bond angles present in the molecule given, we will use the Vesper model. We need to define first what are the central atoms present in this molecule. The nitrogen and the carbon-nitrogen-hydrogen bond is one of those, and another is the nitrogen-carbon-nitrogen. Let's start first on the carbon-nitrogen-hydrogen bond. This form follows the AB3E because of the presence of 3 single bonds and 1 lone pair. This follows the geometric form of trigonal pyramidal. I can never say it. Whatever. And because of the presence of the lone pairs on the nitrogen, this carbon-hydrogen-nitrogen angle becomes 109.5 degrees. Yep, so that's what I had as well. And the second central atom is the nitrogen-carbon-nitrogen bond. So they rewrote it. So they did it a different way, and they actually just reconfigured it to have 2 double bonds. But it is still doable to find out the bond angle if you just kept it at the same structure. So anyways, I'll still continue to read. Vesper model lets us treat double bonds present as single bonds. This form compromises of 2 bonds and 2 lone pairs, having the form of AB2E2. Because of this, we will have a molecular geometry called bent. 2 lone pairs make the angle on the nitrogen. No, the structure is also incorrect because you can see that carbon has 2 double bonds and also lone pairs. So that is more than it needs. So you will rarely see carbon have 4 bonds and also lone pairs. So I'm just going to say the first part is correct. And then I'll take note and write down kind of the mistakes of the second part. Okay, so I just said that the first part is correct, how it's a trigonal pyramid. 109.5 degrees. And however, the structure for the second part is incorrect. We can keep the intended structure and see that the carbon has 2 bond pairs and 0 lone pairs. This gives us a linear molecular geometry and electron geometry, and a predicted bond angle of 180 degrees. Okay, so on to question 2. Which should be the stronger acid, HOCN or HCN? Explain briefly. Okay. So let's write the structure of both of these acids. So the difference is that one of them has an OH group, and because of this oxygen atom, since it is more electronegative than the hydrogen, it induces a positive charge on our hydrogen atom. So we can also show where the partial charges would be. So because there's a positive charge on this hydrogen atom, this makes it more readily removed when you place it in the water. So therefore, HO0N is the stronger acid. So I'm just going to write down my explanation. So because oxygen is more electronegative, this induces a positive charge on the H atom, making it more readily removed. When placed in water. Okay, and if we look at the carbon and hydrogen bond, it doesn't have that same effect since carbon and hydrogen have similar electronegativity values. Okay, so let's see what the junior tutor said. They use a different approach using the Ka values. So the Ka is also the acid dissociation constant. So let's see what they said. The strength of the acidity of a compound is determined by the ability of the compound to release its acidic hydrogen. Yep, so that's correct. And the bigger that value of Ka, the stronger the acidity of the compound. In this case, HOCN has a higher value of Ka, which concludes that it is a stronger acid than HCN. Yes, so that is correct as well. In the case of both, the acidic hydrogen is connected differently between the two compounds. The acidic hydrogen of HOCN is connected with the oxygen, which is an electron withdrawing atom. Basically, the acidic hydrogen can be easily released. On the other hand, the acidic hydrogen in HCN is connected to carbon, which is an electron donating atom. to hydrogen, which makes it harder for the hydrogen to be released. Yep, so they showed both approaches. So this solution is correct. Okay, so I just kind of rewrote what I said already. And we can move on to question number 3. How do you find the molar mass of argon gas? So luckily for us, argon is just a single element that you can find on the periodic table. And on the periodic table, they'll give you different values. The main ones are the atomic number, which gives you number of protons, and the atomic mass number, which is what we're looking for. So if we look at our periodic table, we'll see that argon has a molar mass of 39.95 grams per mole. Okay, so let's see what the junior tutor said. Argon is the element that is present in group 18 and period 3 of the periodic table. Note that the relative atomic mass from the element box of argon in the periodic table, the relative atomic mass is 39.948 as shown in the following figure. Okay, so now they went into detail about how one would find relative atomic mass. So in other words, it's pretty much finding the average mass of all the different isotopes of that element. And yeah, they showed the whole calculation. So I could say that this solution is correct. Okay, so now moving on to question number 4. Draw the correct products for the following reaction. So we have this triple bonded carbon functionality. Okay, so if we wanted to try to name this, you'll see that there are 5 carbons, and if we numbered them, we'd see the triple bond is on carbon 2, so this would just be called penta 2-ine. So the ine is to tell us that there is a triple bond. So this reacts with H2 and this P2 catalyst, which is nickel based. So when we have H2 reacting with a metal catalyst, what typically happens is something called hydrogenation. So as you can guess from the name, it has something to do with the two hydrogens, which is understandable. But basically, when you have a hydrogenation reaction, this is the addition of molecular hydrogen, so the H2, across a double or triple bond. So this reduces them. Okay, so this catalyst in particular, this P2 catalyst, allows for syn addition. So what this means is that our hydrogens will be added on the same side. So the way that I like to remember is that syn starts with an S and same side starts with an S as well. So yeah. And if we were to draw the product, so notice that there's only one molecule of H2. They didn't really specify the amount. So let's just assume there is only one H2. The triple bond gets reduced to a double bond. And we can draw our newly formed hydrogens on the same side. Okay, so the structure would look something like this. So now, if we wanted to name this structure to show that the hydrogens are on the same side, we would put a Z in brackets, and then the name of the structure, which is pent 2-ene. Okay, so let's see what the junior tutor said. The reaction above shows an alkyne, penta-2-ine, reacting with hydrogen in the presence of P2 catalyst. The P2 catalyst allows for the syn addition of hydrogen across the triple bond. Since only 1 mole of hydrogen is the product, it will be, okay, so since only 1 mole of hydrogen is added, the product will be an alkene, which is Z-pent-2-ene. The structure is shown below. Yep, so this solution is correct. Okay, so question number 5 asks, how do I know if a double displacement reaction occurs? Okay, so double displacement reaction. So just a brief definition. This is when parts of two ionic compounds are exchanged. making 2 new compounds. So it's easier just to show what this may look like in a general reaction. Let's say we had 2 ionic compounds like AB and CD. In a double displacement reaction, if these were to be separated into their ions, so let's say they look like this. Then they would all just kind of switch partners. So the positively charged A will react with the negatively charged D, and this negatively charged B would react with the positively charged C. So you kind of get something like that. Let me just erase this. Okay, so we know we have a double displacement reaction because these typically occur when one of the products is water or a gas or a solid. Okay, so let's see what the junior tutor said. A double displacement reaction occurs when 2 compounds can be ionized so that it can react interchangeably. When an ionizable compound reacts with another ionizable compound, chemical reaction equation would be, okay, so here they show the charges. AB plus CD makes AD plus CB. The insolubility of one of the products is needed in order to retain the double displacement reaction, or else the ions will remain as ions in aqueous solution. So this solution is correct. Products can also be a gas or water. Okay, so this question has a temperature composition diagram, and it asks, what is the mass percent of hexane in a mixture with heptane if the mole fraction of hexane is 0.20? And then they show this temperature composition diagram. Okay, so let's try to answer this question. So this is question number 6. Okay, so they give us the mole fraction of hexane. So to help us answer this question, step 1 is to assume that we have 1 mole of the total mixture. So this will help us calculate the mole fraction of heptane. Okay. So I'll just write down an explanation, just like a sample equation showing how mole fraction is calculated if we had the mole fraction, which can be denoted as X, the mole fraction of A, this is equal to the number of moles of A divided by the total number of moles. Okay, so then if they gave us the mole fraction in the question, then we can calculate how many moles there are of hexane. Okay, so I just showed that if we assumed 1 mole of the total mixture, then there is 0.2 moles of hexane in the total mixture. And like I mentioned earlier, because we know the mole fraction of hexane is 0.2, we can calculate the moles of heptane. So I'll put mole fraction of heptane is equal to 1 minus 0.20. Since we know that this mixture only contains hexane and heptane, if 0.2 of that, of 1 mole of the total mixture is hexane, then we know the remaining 0.8 will be heptane. And then since we know the mole fraction, we can also just write that the moles of heptane is 0.8 moles. Okay, so now that we know the number of moles of both of these gases, step 2 is to find their molar masses. So let's say we didn't know the molar masses of these compounds. Let's just quickly draw them out. So for hexane, this is a 6-carbon chain. So there's no double bonds or anything. And we're just going to fill in the rest of the bonds with hydrogens. So there are 6 carbons and 14 hydrogens. So if we were to find the molar mass of heptane, it would be the molar mass of carbon times 6 plus 14 times the molar mass of hydrogen. Okay, so this gives us a molar mass of 86.2 grams per mole. So if we wanted to do the same thing for the heptane, then it would be 7 carbons and 16 hydrogens. So this would give us a molar mass of 100.2 grams per mole. Okay, so let me just try to separate the different parts. So step 3, now that we have the number of moles and we have the molar masses, we just need to find the total masses of both of the gases. So let's recall that mass is equal to the number of moles times the molar mass. So the mass of hexane would be 0.2 moles times 86.2 grams per mole, which gives us around 17.2 grams. And the mass of heptane is 0.8 moles times 100.2 grams per mole, which gives us a much larger value, around 80.16 grams. Okay, so the question asks for the mass percentage of hexane. So we have everything we need to calculate this. So the mass percent of hexane is equal to the mass of hexane divided by the total mass of the gases. So I did not leave myself a lot of room, but we know the mass of hexane was 17.2 grams, and the total mass is just the 17.2 plus the 80.16 grams from the heptane. All of this times 100. I'm going to write it up here. Gives us a value of 17.7%. Okay, so let's kind of fit that in the corner. So the answer is 17.7 mass percent of hexane. So now let's see what the junior tutor said. To assume 1 mole of the mixture, the mole fraction is equal to the mole A divided by the moles in solution. Okay, so 0.2 is equal to the moles of hexane divided by 1. So moles of hexane is 0.2. Moles of heptane is equal to 0.8. Considering the following molar masses, for heptane they had 100.12, and for hexane they had 86.18. And then they found the masses of both of hexane and heptane. So around 80.096 grams of heptane and around 17.236 of hexane. And they found the mass percent by doing the mass of hexane divided by the mass of the mixture. And they also got around 17.71%. Yep, so I can say that this solution is correct. Okay, so now let's move on to question number 7. So this asks, what is an example of a combination reaction? So a combination reaction, let me just write out a brief definition. This is when two or more elements or compounds combine, hence the word combination, to form a single product. Okay, so just like for a general example, if you had x plus y, this makes xy. So the question just asks for an example. So one of the examples could be iron solid plus oxygen makes this iron oxide, also known as rust. Okay, so let's try to balance this equation. So you can see that there are two oxygens in front. Well, there are two oxygens in the reactant side and three oxygens in the product side. So an easy way to balance one of these questions is to just put the coefficient as the same value as the subscript of the opposite one. So let's say we had 2O2 here. I'm going to put a 2 in front of the iron oxide. And then we have Fe2O3. So I'm going to put a 3 in front of O2. So this gives us a total of 6 oxygens on both sides. So now I can balance my iron easily. So I see that there are 4 irons on my product side. So I just need to put a coefficient of 4 in front of my iron solid. This is an example of a combination reaction. We have two elements, iron and oxygen, coming together to form this Fe2O3. Okay, so the junior tutor said that a combination reaction involves elements or compounds that are combined and forms a single product. Basically, bonds are formed from one element to another. An example of a combination reaction is 2CO plus O2 makes 2CO2. Yep, so this solution is correct. Okay, so question number 8. How many valence electrons does each member of the boron family have? Okay, so if we were to find boron on the periodic table and write down its electron configuration, it would be 1s2, 2s2, 2p1. So boron has a total of 5 electrons. So if I were to kind of draw the structure of what the electron shells might look like, 2 of those electrons will be on the inside, and then the remaining 3 would be valence. So therefore, boron has 3 valence electrons. So all of the elements in the same column as boron will also have 3 electrons. Let's look at a periodic table. So boron, where's the boron is found here. So aluminum and all of the elements below it would also have 3 valence electrons. So let's draw aluminum as an example. If you see here, yeah, so it's hard to read. Let me just try to find a more clear one. I'm just trying to see the all the atomic numbers of each of these elements. So if you can see here, boron has 5, aluminum has 13. So again, it will have 2 electrons on the most inner shell, and then it's going to have 8 in the middle. So that's 10, but aluminum has 13. So again, it has 3 electrons. So the only difference between boron and aluminum is that aluminum has 8 more electrons, and its atomic radius is therefore bigger than boron's because it has more electrons. Okay, so let's see what the junior tutor said. The boron family in the periodic table is the elements from boron all the way to the bottom of the column of the boron element. The highest orbital of the boron family is the S2p1 orbital, and the superscripts in the orbital show the number of electrons present in the outermost shell of the element. Thus, the boron family has 3 valence electrons each. Yep, so this solution is correct. Okay, so on to question 9. Write the electron configurations of phosphorus and chlorine using both SPDF notation and orbital box diagrams. Describe the relationship between each atom's electron configuration and position in the periodic table. Okay, so this version of the periodic table kind of highlights the S, P, D, and F orbitals. So if we were to write down the electron configuration of phosphorus, it is found here, atomic number 15. To write the shorthand configuration, we would put the noble gas that comes before it in square brackets. So in this case, it is neon. And then we just kind of continue starting from sodium, writing 3s2. So because it is in row 3 and the block number is S, and then we just continue writing 3p123, 3p3. So up to the phosphorus. And let's do the same thing for chlorine. Chlorine is found here. So it would also be just neon, 3s2, 3p, 1, 2, 3, 4, 5. Okay, so we need the orbital box diagrams. So I'm just going to draw this showing like the energy as well. So 3s is here. 3p is a higher energy. And if we were to fill in the electrons, we would have 2 in the s orbital and then 3 in the 3p orbital. And similarly for chlorine, 3s would be down here and 3p would be up there. So there are 2 in the s orbital, and now we have 5 electrons in 3p. Okay, so notice that phosphorus has 3 valence electrons. Well, there are 5 in total, and chlorine has 7. So looking at the atom's electron configuration and its position in the periodic table, phosphorus has 5 valence electrons. And if we look at the periodic table or any periodic table, you'll see that it is in column 5 or period 5A. And the same thing for chlorine. There are 7 valence electrons, and it is found in period 7A. So that's something to help try to remember how many valence electrons there would be. And the junior tutor said the period of location in the periodic table corresponds to the valence shell's principal quantum number. Number of electrons correspond to the number of main group elements they are in. Phosphorus has 5 valence electrons and it is in the 5th main group. Chlorine has 7 and it is in the 7th main group. Yep, so this solution is correct. So question 10 just asks, what is the Bohr model of the lithium atom? So lithium, it has atomic number 3. So therefore it has 3 protons and also 3 electrons if it was a neutral atom. So if we were to draw its Bohr model, we'll draw 2 electrons in the inner shell and then 1 in the valence. Okay, so this is the Bohr model of a lithium atom. So the junior tutor said lithium is in period 2, so it will have 2 occupied energy levels. It is in group 1, so it will have 1 electron in the valence shell and they drew it as well. Okay, so this solution is correct. I think we have time for one more question. Give 3 examples of gaseous elements that exist as diatomic molecules, and give 3 examples of gaseous elements that exist as monoatomic species. So as you can assume, diatomic molecules, because it has a prefix of di, that means there is 2 of it. So 3 examples of diatomic molecules would be like H2, N2, or O2. And for monoatomic, since it has a prefix of mono, that only means 1. Like when you have a monocle, there's only 1 lens. So examples of monatomic, not molecules, but species. This would be like our noble gases such as neon, argon, and helium. Since they are noble gases, you don't really find them reacting with other elements as much, so that's why they can be found as monoatomic species. Okay, so the junior tutor said diatomic gaseous elements are as follows: hydrogen, nitrogen, fluorine, oxygen, iodine. I don't know about carbon, and boron. Monoatomic gaseous elements are as follows: helium, radon, neon, xenon, argon, and potassium. Yep, so this solution is correct. Okay, so if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you wanted to submit a question of your own, then check out the links in the description. And also, don't forget to give this video a thumbs up and a comment if you enjoyed it. And you can share it with your friends and classmates if you needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.